The leveling process measures elevations for mapping and for solving problems. In this video, we'll use another leveling method to begin designing a waterway improvement. I'm Todd Horton for the Illinois Professional Land Surveyors Association. In the last video, you saw the field process and note-keeping for a benchmark leveling circuit. Also called a differential leveling circuit, this survey used multiple instrument setups, and at each setup, the surveyor measured one backsight and one foresight. In keeping with the adage, measure twice, cut once, the level circuit had a forward run and a reverse run. Because this level circuit ended where it began, we call it a closed loop circuit. Since there was only one known benchmark available, all the elevations in the survey are measured relative to that one benchmark. Let's suppose two known benchmarks are available near your project site. You plan to create a new benchmark, but which known benchmark should you use for your survey? Benchmark A or benchmark B? If benchmarks A and B were created in the same original survey, then you can use both. Start the level circuit on A and end the circuit on B. We call this a closed link circuit. That is, your new level circuit links between two known benchmarks. Link and loop level circuits both begin and end on known benchmarks. Ending on a known benchmark makes the level circuit closed. At the closing benchmark, you can compute the closure error in the circuit. If there are closed circuits, then it's possible to have an open circuit. In surveying, an open level circuit does not end on a known benchmark, so it contains no check for blunders and errors. For instance, if we skipped the reverse run of the closed loop circuit from before, it would instead become an open circuit. Because an open level circuit does not self-check like a closed circuit, you should always use closed level circuits. So far in this video series, we've explored benchmark leveling. It's a great place to begin learning, but there is a more common leveling method we use to solve all kinds of problems. Imagine that your farm has a grass waterway like this one. When properly constructed, this waterway reduces erosion, prevents ponding, and allows easy travel by vehicles and machinery. The waterway profile, that is, the changing slope along its path, must harmonize these goals. However, your waterway has a ponding problem. So how do we begin to solve this problem? We can use a method called profile leveling. The idea is to measure the elevation at intervals along the waterway profile. Equipped with this information, we can design a new waterway profile and excavate the soil that caused the ponding problem. Here's a simplified map of your waterway. Computing waterway slope requires not only elevation difference, but also horizontal distance. For simplicity, we use a system called stationing to indicate horizontal distance. Very similar to mile markers along a highway, stations tell us the distance from an origin point. We'll mark the low end of the waterway with a wood stake labeled with station 0 plus 0, 0. The plus sign in this station is a placeholder between the tens and 100s places. The plus sign identifies this number as a location, just like the highway mile marker. By measuring along the waterway center line, we can mark a new station every 100 feet. Remember, the plus sign in this station is a placeholder between the tens and 100s places. So when we've measured 100 feet from the 0 plus 0, 0 origin, we can mark that as station 1 plus 0, 0. Station 2 plus 0, 0 is 200 feet from the origin. Station 3 plus 0, 0 is 300 feet from the origin. This system allows more specific locations as well. The deepest ponding in your waterway occurs at station 6 plus 72. Station 6 plus 72 is 672 feet from the 0 plus 00 origin. Now that we have the stations marked, it's time to use profile leveling to measure the elevation at those stations in the waterway. We'll set up our instrument where we can see the starting benchmark and several of the station marks. Our first rod reading is a backsight on the benchmark, and our first foresight will be at station 0 plus 00. Instead of moving the instrument like in benchmark leveling, we can continue reading the rod at the next station marks. When distance or obstacles prevent us from taking more readings, then we'll establish a turning point and measure a foresight there. Remember that in benchmark leveling, for every instrument setup, there is one backsight reading and one foresight reading. However, in profile leveling, for every instrument setup, there is still only one backsight reading, but there can be several foresight readings, as you see here. This is the primary difference between benchmark leveling and profile leveling. After reading the foresight at the turning point, we'll move the instrument where we can see the turning point and the remaining station marks. With a backsight reading taken at the turning point, we're ready to read foresights on the waterway stations. There is another benchmark nearby, so we'll close our level circuit there with a final foresight reading. Since we didn't return to the starting benchmark, this is now a closed link circuit. That's how the process will look. Let's wade deeper into the water and explore proper note keeping and computations for profile leveling. Just as before, our notes will have the standard 5 column headings for station, backsight, height of instrument, foresight, and elevation. Benchmark A has a known elevation of 585.95 feet recorded in the elevation column in a new row labeled Benchmark A. The backsight reading goes in the backsight column on that same row. It's a good idea for learners to mark a dash in the foresight column now. This can prevent recording a foresight reading in the wrong place. Our first foresight reading belongs in the next row, labeled here as station 0 plus 00. Each new foresight gets its own new row. Now we'll start our computations. Since all 6 of these foresights were read from the same instrument setup, we'll use the same HI value for all 6 elevations. Watch this. By adding the backsight reading to the benchmark elevation, we get the HI of the first setup, 595.28 feet. The HI is the elevation of the instrument line of sight. Subtract the first foresight reading from the HI to get the elevation at station 0 plus 00. Then subtract the next foresight from the same HI for the elevation at 1 plus 00. Repeat this process for all the foresight readings corresponding to that HI. Since the last foresight from the instrument setup is a turning point, we'll read the backsight for the next setup at that same turning point. Since we created the turning point row during the first instrument setup, we'll now record the next backsight in that same row. Once again, we'll add the backsight reading to the turning point elevation, and we get the HI of the second setup, 601.24 feet. From this new HI, we'll measure the foresights to station 6 plus 00 through 10 plus 00. Since the second setup has a new HI, we'll use that HI to compute all the foresight elevations according to this setup. Now, the final closing rod reading is on our ending benchmark. It may be tempting to call this a backsight, but actually it's a foresight. Remember that there is only one backsight instrument setup. For this setup, we took the backsight reading at the turning point. Therefore, the rod reading on the ending benchmark is a foresight. Benchmark B had a known elevation prior to our survey. It is common practice to show the known elevation of the ending benchmark in parentheses adjacent to the measured elevation. As we discussed in an earlier video, the difference between these values is our circuit closure error. This is a good time to illustrate an important note-keeping pattern. Notice that the foresight on turning point 1 was taken from the first setup. Therefore, the elevation of turning point 1 is computed from the first HI. The row for turning point 1 also contains the backsight and HI for the second setup. And the elevation of the closing foresight is computed from the final HI in the circuit. The arithmetic check for profile leveling requires careful attention. First, let's review the arithmetic check for the benchmark leveling circuit in the previous video. That circuit had 10 setups. How can we tell that from the notes? Well, simply by counting the number of HIs. Remember, there is only one HI per setup. Since there is only one backsight per HI, then there are 10 backsight readings. And since a benchmark circuit has only one foresight per setup, then there are 10 foresight readings. For our arithmetic check, the number of backsight readings and the number of foresight readings must be equal. So now for profile leveling, the same pattern applies. In our profile leveling circuit, we had 2 setups and thus 2 backsight readings. Here, the sum of the backsights is 16.95 feet. Now we need to sum 2 foresights. But which 2 foresights must we choose? If we add up all 13 of them, that total just won't be reasonable. So here's the rule for selecting the correct foresights. Use only those foresight readings taken at turning points and at benchmarks. The foresights taken on the profile stations do not affect the closure of the circuit. Thus, applying this rule, the sum of foresights on our turning point and benchmark is 5.23 feet. Here you can see that our arithmetic check confirms that the closing elevation in the field notes is correct. If these 2 results don't match, then there is an arithmetic blunder that must be found and corrected. So now, armed with measured elevations in your waterway, we can design a new waterway profile and excavate the soil that caused your ponding problem. Profile leveling makes the solution possible.
Now that you've seen the fundamentals of leveling, it's time to explore quality control. In the next video, we'll look at quality standards, error management, and instrument calibration. I'm Todd Horton for the Illinois Professional Land Surveyors Association.